In this video, we wish to look at how it's possible to carry sound on a wire. And in order to do that, we're going to take a look at a simple analogy from childhood. This is the analogy that Alexander Graham Bell and Elijah Gray had to pull upon when they were first trying to figure out how to invent the first telephones. So when you have two tin cans and a string, you punch holes in the bottom of the two tin cans and you thread the string through and tie it off in a knot. Then when you pull the string taut and it's tight, one person can speak into one end and you can hear the voice out of the other. The reason that this is possible is because the mechanical energy of the person's voice hits the bottom of the tin can and resonates, vibrates that string just a little bit. If the string is being held tight, that vibration is carried across the string to the bottom of the other tin can. The string basically pulls and tugs at the bottom of that tin can, reproducing the sound waves that the person is speaking in on the other end. So it's a direct translation of the mechanical energy of the sound waves into string being pulled and carrying that vibration over to the other tin can. So when we look at how a telephone works, it's a similar kind of idea but implemented very differently. Here's a handset that contains a mouthpiece with a microphone and an earpiece that has a speaker. And when a telephone call is placed, a connection is made between the caller and the receiver. Picking the handset up off the switch hook actually closes a circuit, forming that connection then between caller and receiver. And the microphone on the caller has a circuit connected to the earpiece on the receiver, and vice versa. The receiver has a mouthpiece that's also connected to the sender's earpiece. So both parties can be talking at the same time and they can hear one another. Well, in order to understand how that device can work, we have to look into how both a microphone and a speaker work to carry sound. We're basically going to translate the mechanical sound waves on the left into electrical signals that are carried on the wire, on the circuit. So here we have a microphone diaphragm. This microphone is a condenser microphone, and we're going to describe something a little bit different called a carbon microphone. A carbon microphone has a diaphragm like this that's filled with carbon granules. Carbon conducts electricity, and so we have a battery with wire connections on each end of the diaphragm so that there's an electrical current, a DC current, that goes through the carbon granules. Now we pick up that current and connect it to an amplifier to strengthen the signal so we can carry that signal a distance over to a speaker that will play it out of the speaker end. Well, as the sound waves hit the diaphragm, the granules of carbon shift a little bit. That shifting of the carbon granules changes the resistance of the carbon. Changing the resistance of the carbon is going to have a direct effect on changing the voltage. On the next slide, we'll look at Ohm's law that describes this phenomenon completely. Ohm's law states that I equals V over R. Now, I is electrical current measured in amps or amperes. V is the potential difference measured in volts, that's the voltage, and the resistance that impedes that current is measured in ohms. Well, the current in that microphone is constant. It's a constant voltage source. It comes from a battery right here. So the current is going to stay the same. So if the carbon granules shifting change the resistance, the voltage has to change in the same manner. If the resistance goes down, the voltage has to go down. And if the resistance goes up, the voltage has to go up in order to keep in balance according to Ohm's law. That can be shown here on a diagram. If we look at the voltage output, the voltage is changing. This change in voltage is basically the person's voice on the wire. So a voltage pattern is the imprint of the sound waves that the person is speaking into the microphone being carried as an electrical signal over to the other end. Here, just by contrast, we have a different kind of microphone. This is called a dynamic microphone. And this one is the magnetodynamic microphone. And it's named so because it works just like the magneto device, those two opposing horseshoe magnets. If you remembered when we talked about how to generate alternating current, we had one fixed magnet and one rotating magnet. And as we rotated the magnet, the change in the magnetic fields interacting with one another created a voltage difference, an electrical current. Well, the same idea is being done here. Notice now, though, we do not have a battery but a large magnet. The magnet is connecting wires in an electrical coil, and then we attach two wires coming from both ends of that coil. Well, the coil has a magnetic field set up in it from the magnet, and when the sound waves hit the coil, the wires move a little bit, and that movement in the wires makes subtle changes in the magnetic field. Just like the two opposing horseshoe magnets, the one that can move can rock back and forth, and that rocking of that magnet can be shown as a motion in the needle on the voltmeter. So here it's interesting that our microphone does not have a battery or any other power source. It's simply using that magneto effect, the interaction of a wire moving in a magnetic field, that's inducing a voltage in a wire. This is essentially the same idea of how an electric pickup works on a guitar. When on an electric guitar, over each string underneath on the body of the guitar, there's a magnet. And when you pluck the string vibrates, and that movement of the string is changing the magnetic field constantly with the vibration. And so that signal's picked up by those pickup leads, and that energy is then amplified and sent out a speaker as well. So here we have the other end. We have to look at how a speaker works, and this is a cutaway view. Speaker has, first off, a large magnet here. This is in the form of a torus or a donut. It's a circular magnet, and it surrounds the back of the speaker and is attached to the cone. On the inside, through the hole in that magnet, we have an electrical coil. Here's a coil of copper wire. We'll connect our microphone leads up to this coil, and when we energize this coil, you know from the left-hand rule, when there's energy in a wire, there's also a magnetic field that surrounds it, given by the left-hand rule. So when we turn the speaker on, and there's energy, electrical current, in this wire wrap, we have an electromagnet. We turn on the power, and a magnetic field is wrapped around this coil. That magnetic field is going to interfere and interact with this other magnetic field given by this round toroidal magnet. The interaction of those two magnetic fields is what's going to make the speaker work. When the signal comes, the voltage difference slightly changes the magnetic field around the inner coil. And as that magnetic field changes, it either attracts or repels the other magnet's field from the torus magnet. An attraction will move the speaker to the right, and a repulsion of the two magnetic fields will move the speaker to the left. This is the magnet that's mounted on the back of the cone, so as the signal from the microphone comes in, we get this back and forth motion in unison with it of this back magnet. That moves the cone, and the cone is pushing columns of air, and that's pushing the sound waves out into the air as columns of air. And that's, in effect, how we hear sounds. When we hear a sound, there's a changes that our ear picks up through changes in the columns of air that's transmitting the sound. So if we put the two parts together, we have the microphone on the left, which is picking up the mechanical energy from sound waves and transferring that into an electrical signal a voltage difference on a wire. We connect and close that circuit onto this coil. The coil is energized, and so in effect it is an electromagnet. The magnetic field changes with the voltage around the coil, and that causes interaction with the magnetic field produced by this ring magnet on the back of the speaker. So the net effect is the sound waves coming in on the microphone on this end are output through the speaker on the other end in complete unison with the change of the sound waves here, meaning the change in the air columns out of the speaker. That's how we hear sound out of the speaker. And this principle of energizing a coil to get one magnetic field is basically the idea of how an electromagnet works. Even in medical imaging, there's something called magnetic resonance imaging, where there's a large electromagnet that's turned on at the start of the imaging process. So the greater the electrical current in the coil, the greater the magnetic field. So when we put that all together, this is the basic principle on how a telephone works. We have a microphone to encode this sound into a voltage pattern. We have a closed connection. When the switch hook is closed, the handset is picked up off the switch hook. We have a closed circuit, and the two connections are between the microphone and speaker on each of the two handsets.